Welcome, Hornets, and thank you for joining me for part 3 of assignment number 10. Please take note that I have altered the assignment slightly with numbers 35 through 37. I'm asking that you only do the odds now since the book is asking you to do 10 iterations using Euler's method. We're going to go ahead and start with number 45, which is talking about a calf that weighs 60 pounds at birth and gains weight at a rate of dw dt equals k times 120 minus w. Now you'll notice that this is the rate of change in the weight is directly proportional to the difference between a constant and the weight. We know this as a restricted growth problem, and therefore we can immediately go to our restricted growth formula. Now if you don't remember how to find that, you're going to want to do the solving the particular solution, but if you know the wording and you can recognize it, this goes directly to W of t is equal to 1200 minus CE to the negative KT power. Now remember, you can put either a minus KT power or a positive KT power, it doesn't matter. The K will always come out to what it has to be. We're now going to utilize the value of our initial weight at time 0 is 60. This allows me to write it as 60 equals 1200 minus CE to the 0 power. Therefore, I end up with 1140 equals my constant, and it is a minus, and our constant. So the negative C is going to equal that. Therefore, the double negative will apply, and 1140 is equal to C. We're now going to rewrite that into our problem. WT equals 1200 minus 1140 e to the negative KT. Now, it's at this point that they're going to ask you to find some graphs and just plug in some values. So they ask you in B to find what is the formula if K is equal to 0.8, then 0.9, and then 1. And this is very straightforward. We get WT equals, or the weight in terms of time, is 1,200 minus 1140 e to the negative 0.8t, and then 1200 minus 1140 e to the minus 0.9t. And the last formula is W of t, or the weight in terms of time, is 1200 minus 1140 e to the t minus t power. Now they're going to want us to now work with these formulas, and then using our calculator, try to figure out how long is it going to take for the calf to weigh 800 pounds. So we're putting 800 pounds here, and we're solving for t. As we solve for t, we end up getting approximately t is equal to about 1.31 years. This is when k equals 0.8. We then find t is approximately 1.16 years. And this is when k is equal to 0.9. Notice how the time is slowly decreasing. T is approximately 1.05 years when k equals 1. And this is just plugging in k, subtracting 120, dividing by negative 1400, which will make it a positive value. We then exponentiate both sides, and then we divide by the negative 0.8. This should give you t. The final question in number 45 is saying, what's going to be the maximum weight? Well, the maximum weight is the limit as our time approaches infinity for each of these equations, and you'll notice that means that this is slowly going towards 0. In each case, we take less and less and less away. Because of that, we know that our maximum for this W of t is 1,200 pounds. And therefore, the maximum weight will be 1,200 pounds. And that's number 45. Let's go ahead and now move to number 53. Now 53 is a deceptively long problem, and I don't want anyone to be having any false impressions. It looks like it's not that big, but it is. It says, at any time t, the rate of growth of the population n of deer in a state park is proportional to the product of n and L minus n, where L is equal to 500, is the maximum number of deer that the park can sustain. They then tell you when t equals 0, n equals 100, when t equals 4, n equals 200, and then write n as a function in terms of time. Alrighty. Now, part of this is going to require us to use our pre-calculus decomposition of fractions. And if you do not remember how to do decomposition of fractions, please go to my Google page and locate the decomposition of fractions review of pre-calculus, which I have done through about 3 to 4 videos. So I've tried to be very extensive so that you are aware. Be aware you are going to need to know this when you move to BC. So here we go. We're going to immediately write our differential using the terms that they've given us. The rate of change of the population is directly proportional to the population and the difference between 500 and that population. We're now going to separate our variables, and as we separate the variables, I'm going to end up with 1 over n times 500 minus n dn is equal to k dt. We then integrate both sides. Before we can integrate this, we have to decompose it, and they have the constant factor of 1 over 500 n minus, double negative, plus 1 over 500, and we have 500 minus n. And this is what we're going to work with. dn is equal to our kt plus c. Now, that means that I can factor out my 1 over 500 and just work with the 1 over n, which we know will be the natural log, plus 1 over 500 minus n dn. Now, I'm going to multiply both sides by this 500 right here so that I get a new 500 times the constant t plus c. That gets rid of this and allows me to integrate so that I end up with the natural log of n, absolute value, minus the natural log of the absolute value of 500 minus n is equal to 500 times kt plus c. Now, this is going to give me an exponentiation process. So I'm going to exponentiate. Now, if you wish, you can go ahead and combine these. You should end up with n divided by 500 minus n is equal to e to the 500 kt, and I have my 500 times c, which is just e to the c, which is simply another constant. Now, it's at this point that things start to get a little bit interesting. We're going to have to cross multiply so that we can get two terms that have n. We'll then move them to one side and factor that n out and then divide. So follow along with me as we slowly go through this. We end up with n is equal to 500 ce to the 500 kt minus nce to the 500 kt. We're now going to factor out, we're going to move this piece over so that we end up with n plus, okay, we're right. So n plus the nce to the 500 kt power is equal to 500 ce to the 500 kt. We're now going to factor out the n, and I end up getting 1 plus CE to the 500 KT equaling 500 CE to the 500 KT. Now, be aware that when I was doing this, I did have that, I ended up with a positive, which I'm going to now divide. So I end up with this n. I get 500 CE to the 500 KT. And then I have 1 plus CE to the 500 KT. Now, don't freak out, because as you go through this process, you're ultimately going to find that your K, that this C value that you're going to get is a negative 1/4. Please don't worry about that. That negative 1/4 is what you would expect, or a positive 1/4, depending upon how it works. So here we go. When we plug in our value of 0 and 100, we are going to end up with 100 equals 500C divided by 1 plus C. This is going to allow me to get 100 plus 100C is equal to 500C, which means that I have 100 equals 400C, and 1/4 has to equal C. We're now going to have to plug that in. So we now have our N is equal to 500. CE, let's put that 1/4 in and multiply, please. So I'm going to end up with, let's make sure I put this in correctly, 125 e to the 500 KT divided by 1 plus 0.25 e to the 500 KT. I'm now going to put in my value of t equal to 4 and n equals 200. And I end up with 200 equals, and I'm now putting in 125 e to the 2000 K divided by 1 plus 0.25 e to the 2000 K, and I'm now going to solve for K. Now, as we do this, we're going to have to cross multiply again, so we end up with this 200 plus 50e to the 2000 K is equal to 125e to the 2000 K. I'm going to move this over and subtract, and I get 200 is equal to 75, and it is e to the 2000 K. Dividing, I'm going to end up having 200 over 75, and if you wish, you can reduce that, or you can change it into a decimal. And I'm now going to have my natural log, and this will equal 2000 K. Dividing gives me 1 over 2000 K, 1 over 2000, excuse me, natural log of 200 over 75 equals K. Now, I found my K, and the K turns out to equal approximately 0.2452T when I put it in, or let's just leave it at that, and it is an approximate value. We're now going to want to put that back into our problem. So we end up with N of T is equal to 125 e to the 0.2452T divided by 1 plus 0.25 e to the 0.2452T. And now we're going to try to clean this up and get it to a reasonable amount. So the way I'm going to work with this is I'm going to start by multiplying the top and the bottom by 4. This is going to leave me with N equal to 500 e to the 0.2452T divided by 4 plus e to the 2452t. And I'm now going to multiply by 1 over e to the point 2452t, 1 over e to the point 2452t. This is going to give me my final answer when I simplify, and it will be n of t is equal to 500 divided by 1 plus 4e to the negative 0.2452t. And that is our goal. And that was number 53. This brings us to number 61. Let's make sure you see that. Number 61, once again, another word problem, says, biology. A population of 8 beavers has been introduced into a new wetlands area. Biologists estimate that the maximum population the wetlands can sustain is 60 beavers. After 3 years, the population is 15 beavers. According to a Gompertz Growth model, how many beavers will be present in the wetlands after 10 years? Now, the Gompertz Growth model is found under example 8, and they do mention this. So if you were reading your book, they give you a direct example in what to do. All right. Once again, this is using a Gompertz growth model, and you'll notice I'm going to end up with something weird like this, and I'm going to have to slowly work through it. So you have your rate of change of y, you have your proportional to the product of y, and the natural log of the ratio. Alrighty, so let's go ahead and take a look at how we use this Gompertz growth model. Following the model exactly, I am going to have the population in terms of time is 60e to the negative c e to the negative kt power. I'm going to put in 8 is equal to 60e to the minus c e to the 0 power, which is 1, and this is going to give me 8/60ths is e to the negative c. Taking my natural log, I have the natural log of 2/15 is equal to negative c. I'm going to bring this, where did my 3 go? I had a time of 3, t equals, hang on. Oh, no, we're still good. This is my c, and it's going to become a negative. Notice you got to be careful working with this. It's easy to make a mistake if you're not careful. Alrighty, here we go. P of t is equal to now 60e to the negative, double negative is going to make it a positive, and I have the natural log of 2/15 times e to the negative kt. We're now going to plug in 15 is y when t equals 3. We end up getting 15 equals 60e to the natural log of 2/15 e to the negative 3k. And we're now going to solve for k. I'm going to divide, which gives me 1/4. I'm going to take my natural log on both sides, and I get the natural log of 1/4 is then going to equal the natural log of 2/15 e to the negative 3k. Now I'm going to divide first so that I have the natural log of 1/4 divided by the natural log of 2/15. Now you'll notice it still equals e to the negative 3k, which means I have to exponentiate again. And I have the natural log of 1/4 divided by the natural log of 2/15 is equal to negative 3k. This is giving me negative 1/3 natural log of, and I have the natural log of 1/4, natural log of 2/15, equaling k, which I'm now going to put into my problem. This is going to give me population in terms of time is 60 e to the natural log of 2/15 e to the power of t thirds. Notice the double negative where I had a negative and the negative became a positive. And I have my natural log of the natural log of 1/4 divided by the natural log of 2/15. And I can now ask, what is the population at 10? Plugging this into my calculator, I am going to get an approximate value, and I am rounding it to the nearest beaver. And therefore I get 34 beavers in the park after 10 years. And that is the end of 61. I hope this has helped. Please remember, if you found this to be helpful, please make sure that you click like. Otherwise, if you have comments or suggestions on how I can improve, please remember to put those comments in so that I can get better at what I do. Please be well and be safe, Hornets. Take care, and remember, it is easy to be mean, so be nice to each other. We can be mean with a look, with a word. We can be mean with silence. We can be mean with an action or with inaction. So it behooves us, and it becomes an important aspect that we be careful in what we do and say, as we do not know how it will impact the people around us. Thank you very much. Be kind, and please be safe. Thank you and goodbye.